Krystal Guo is our next speaker, and she's also going to talk about it a little bit, among other things. She's an assistant professor at the University of Amsterdam, and we're looking forward to her talk.
Thank you, Rafaela, and thank you to the other organizers as well for inviting me to speak here and to participate in this very nice looking workshop. So I work in algebraic graph theory, and I work mostly with eigenvalues of graphs and association schemes. More recently, I have worked on some hypergraphs, but I'm not ready to speak on this work yet. In particular with Josh Cooper that Ida referenced in her slides, we're doing some enumerative aspects of the characteristic polynomial of the tensor version of the hypergraph matrix. And then there's some other work with combinatorial Laplacians that I will reference later. But I thought that since we are all from different areas, from what I could tell from the attendance list, that it would be nice to maybe just introduce the type of algebraic graph theory or the type of mathematics that I do, and then hope that we could form some collaboration or find some common ground during this week or next week. Okay, so mostly I work with algebraic graph theory, and let us just have this slightly maybe boring story now that we're two talks in, that we have the situation where we have a graph, and then, sorry. Okay, and then we summarize its adjacency information in an adjacency matrix, which sort of yeah, so you have an if you have an edge in the graph, like this edge that goes between the red vertex and the green vertex, then the corresponding entry indexed by those vertices should be a 1 and a 0 otherwise. And even though this is just sort of an array in which to store the data about the graph, you can consider this as an operator on your vector space and use the eigenvalue of this operator to bound many things. And to establish many nice properties of graphs. Okay. In the application that I work on, we work with a similar situation wherein instead of a graph, we have a quantum circuit, which is nevertheless encapsulated by some sort of matrix, which I will say more about in the next few slides. And there we want to do the same sort of thing, that it turns out that this matrix that we work with, it is in the same matrix algebra as the association scheme for some models of quantum walks. But in any case, it is some matrix that is defined on an underlying graph in various ways. And then here, what you want to do is to use properties of the transition matrix to give you properties of the quantum walk. And it turns out that this usual classical spectral information, tools and information from this setting also transfers to the properties of the quantum walk. So that's hopefully the broad strokes of what my research is about. So now what I want to do is to give a basic but very high level overview of what this matrix is and what this connection is, and something like this, and to give sort of like a story of how this field, this applications of algebraic graph theory in quantum walks is evolving, to tell you the story of one of the topics that we work on. Okay. Oh yeah, so maybe the nice thing for graph theory is that we're using these tools to study this quantum situation here, but in order to model some aspects, some properties that we want, we actually end up having to define new spectral invariants, spectral graph invariants that are rather interesting. They are just classical, that you could have also defined it without ever knowing what a quantum walk is, but we did not, because it was not a parameter that was interesting before. But now we have sort of a new source for interesting topics. Okay, so yeah, in particular that one. Right, so maybe the first thing, the first type of quantum walk is the following, that approximately this is a quantum computer. Maybe you remember some diagrams of classical computers from your computer science introduction days in high school? No, okay, like a circuit diagram, but this is a quantum circuit diagram. So you have some qubits, And during your quantum algorithm, some stuff happens to them. And then at the end, you measure. This is a measurement symbol. Okay? So what are the stuff that can happen to them? You have various quantum gates, which are like your logic gates, but they're different, I guess. For example, you have control, control, not. You have a Hadamard gate, control Hadamard, quantum Fourier transform of 3 dimensions. So some stuff happens to your qubits, and then at the end you measure. But for a mathematician, the relevant thing is that the stuff that happens to your matrix is a unitary operator. Okay, so all that we care about is this matrix U. So in particular, we care about what kinds of matrices are a U such that this would arise. And then we want to prove properties about the walk using this U matrix here. So sort of a priori, if you just have this system with n qubits, then this U matrix, it should be 2 to the n by 2 to the n, because you have this number of qubits. But in our model that we work with, so we choose a specific Hamiltonian that is in the area, in the single excitation subspace model. And there you can reduce to an n by n matrix. In particular, this matrix, where this is the adjacency matrix of the underlying graph. If you use different interactions between your qubits, like an XYZ interaction, you can replace this with a Laplacian, which is also a natural thing to look at. Okay, right. So maybe we will not give an overview of this and skip this slide because we have a limit on time. Okay, so why do we want to study this? Because this sort of is a prototypical example of what a quantum algorithm looks like. A quantum algorithm is really that you have some qubits and stuff happens to it, and then you have the measurement, which is the output. And then from this measurement, you determine what to output. So if you were trying to use a quantum computer to solve a decision problem, you would set up your circuit, and then based on what you measure here, you output yes or no. So this is sort of how they work. And then what a very seminal paper in this field is that quantum walks can be regarded as a universal computational primitive with any desired quantum computation encoded entirely in some underlying graph. So there are many variants of this. I think in his paper, this specific statement is for the continuous time quantum walk that we look at in this talk, but it is also true for various models of discrete time quantum walk. People have proven the result directly, that that is also a computational primitive where every algorithm can be viewed as some discrete walk. But also like the equivalence between these statements has also been explored by various papers. But maybe there is like a limiting thing that, yes, you can encode any algorithm as a quantum walk, but maybe some algorithms, it's easier to study them without encoding them this way. And sort of what you can also consider is that the things that we are doing, they're like components that you might want to use in a bigger algorithm. So yeah, there are various aspects. But maybe let me just tell you what the matrix is that we want to look at. So the matrix that we want is this transition matrix that changes the state of your quantum walk. And it is just x of ita, where this is like e to the x, and I is a root of -1, t is a variable for time, and a is the adjacency matrix. So this is a matrix valued function in time. Okay. How do we compute e to the matrix? We just take the Taylor series. So this is something that exists and you can write it down. Okay, so maybe some illustrative examples or pictures. So we can evolve a quantum walk on some underlying graph. And in this case, we can evolve it on our C5. And now, what do I want to do? Well, I want to consider sort of the amplitude of my walk, having started at the blue vertex, and I want to measure it ending at the red vertex. So this entry, if I would take the norm squared, that's a probability of measuring at the red vertex, having started at the blue vertex. And if I run it for time 100, this is what it looks like. So what is this? This is a curve in the complex plane parameterized by time. And it's just the entry in this matrix for the times between 0 and 100. Right? Cool. If we run it for a bit more, which is to say, we just force Sage to plot some more points, it looks like this. Cool, right? So there are some things about the walk that clearly maybe relate to symmetries of the graph, or in this case, symmetries of the eigenvalues of the graph. And if you allow it to run for even more time, then it sort of fills in this shape here. Because the entry of this matrix, it will be an almost periodic function. And yeah, this is the sort of embeddings that you get when you project into two space. Okay, so maybe some more context is a specific algorithm that does run on a quantum walk, where it's actually natural to view it as a quantum walk, is the problem of quantum search. So maybe you have already heard of the of quantum search, but it's the situation where your problem is that there are n boxes, one of which is marked. And you can query, so you can open a box and ask, is this the marked box? So that's your operation. And then how many queries, how many steps do you need to find the marked box? So classically, you do need n operations, because it could be in the last box. There's just no faster way, even using randomness, to locate this box faster than linear in n. Okay, and then there is Grover's landmark result, a very famous result in quantum computing, that there is a quantum algorithm that can do it quadratically faster. Okay, so this is the, yeah, and what is equivalent to is running a quantum walk on some underlying graph. And in this case, is a complete graph on n vertices, where n is a number of boxes, one of which is marked. And then the marked vertex has this extra business on it. And the model of the walk that is used actually requires the Laplacian matrix in this case. And there is a weight on this vertex. But the thing is, you don't know where this marked vertex is, and you must detect that after that amount of time. So this algorithm, it really is that I execute the quantum walk on this graph. And after this amount of time, I measure the whole system. And with high probability, I should find my vertex. And that is what Grover shows in his algorithm. And this sort of search is used in Shor's algorithm for factoring. That it is also you set up some sort of situation where the query complexity will be similar. Okay, but spatial search is what we call the problem, where you have an analogous search on a marked graph, but the graph doesn't have to be complete. So maybe the correct way to think about it is to reach back in time and remember when we had like a phone book. Do we know what a phone book is, young people? No, okay, so like in the olden days, when you had to look up someone's phone number, there was like an enormous book, and then you look up their name, and then you look up their phone number in a huge book. Nod? No. But we know what it is, right? Okay, so then the search problem is that you know a phone number, but you don't know whose phone number it is. So now you have your phone book and you're just opening it at random to see if you magically find the person whose phone number you have, right? That's search. But if we're really doing this in real life, well, okay, not in real life, but because we have Google. But you know, if you're really doing this with a phone book, you might say that there should be a cost to turning pages. Like if I'm already on some page and I look for the phone number here, it doesn't cost me that much effort to look at the phone number under it to see if that's the correct number. But if I want to flip to different sections, then maybe this is something that should cost you, right? So that's sort of what's happening in your spatial search, that if you had the complete graph here, it means that I can go to some vertex and ask, is this the marked vertex? And then at the next step, I can go to any other vertex and ask. But here, you're somehow saying that moving to another vertex, it has a cost. And I cannot go directly to all possible vertices. So in particular, I can only go to a vertex that is connected to my current, that has to be a neighbor of my current location. So then this problem is the generalization of quantum search, and it's what we call spatial search. And is not known for which graphs. Spatial search has quadratic speedup. And it could be that for certain very restricted classes of graphs, there is exponential speedup, which is a very interesting thing, obviously, for the quantum community to exhibit that quantum things are exponentially fast, not just quadratically, but exponentially faster. So for search, I don't know of a result. But I'm also not a quantum computer scientist. I just work in the area. I don't know of a result where spatial search has exponential speed up, but there are other quantum walk algorithms where you have you have a very specific setup, and there's a result of Childs and co-authors where you can have exponential speedup with a continuous time walk. And there also is a specific example with a discrete time walk where they can make a very contrived problem on a very contrived graph where the quantum algorithm is exponentially faster. So this is sort of the big picture of the types of things that people who actually do quantum algorithm study. We as mathematicians, we just provide some mathematical tools with which to study these types of things. So hopefully that has given some context, and if you were scared off by the quantum in the title, this is all that it is. Now we will proceed to having pictures and matrices, okay? So the U matrix, this important transition matrix, and this little reduced version that we have, it's sort of not the matrix that records the probabilities. The one that does that is this mixing matrix. So here I have a very small graph consisting of 3 vertices, the path on 3 vertices, and then I have a matrix of the quantum walk on it. And this column is the column corresponding to vertex 0. And it is the entry-wise product of U with itself. And this thing is at time 0. So what this thing says is that if I start at vertex 0, then after 0 amount of time, I'm 100% likely to measure at vertex 0. That makes sense, right? And 0% because I'm not at the other vertices. Okay? So now we allow time to evolve. This is a continuous time walk, but my computer is inherently discrete. So we will be incrementing time discretely by 0.25 each time. Sorry, guys. So yeah, ignore this. So after 0.25 amount of time, this is what that matrix looks like. It is maybe not easy to see, but it's reflected in how red the vertices are. So after a small amount of time, there is non-zero probability, this is slightly pink, of moving to some, measuring at another vertex. And after even more time, now you're only 77% likely to measure at this vertex and 21% at this vertex and close to 0 on the last vertex, right? So is the diagram clear? Because now we will not have the matrix anymore, and we will just record the information in the amount of red in the dots. And now we will allow the time to go. It's moving. So this is what it looks like. We're watching a quantum walk. Yeah, I had Sage draw these diagrams for me, so it will stop. Okay, here we go. So maybe when you were watching that very crude animation, you noticed that we started like this, and there was a time somewhere in the middle where it looked like this situation here, where these 2 vertices were white, and the last thing was red, right? That was like a thing that happened. So this is called perfect state transfer when you start at a vertex and then after some period of time, you're 100% likely to measure at some other vertex. Then we say there's perfect state transfer between these 2 vertices. And this is useful for building quantum algorithms because you can pass the state completely from one vertex to another. So this is some a very fundamental, it's not a specific algorithm that does search or something, but it could be part of such algorithms. So this is a property that we would like to study. The formal definition is just that there exists some time. The probability of measuring at site B after starting at A is 100%. Okay, so Chris Gotzel, who was my master's supervisor and postdoc supervisor, he started trying to do algebraic graph theory with on quantum walks around that time. And what he showed is that the only paths on which there is perfect state transfer, they are P2 and P3. So we just saw P3 and the graph on 2 vertices with a single edge that also has this property. So this thing is very rare, which is a bit sad. Okay, so then he defined this thing called pretty good state transfer from A to B, which just says that you don't have perfect state transfer, but it's pretty good. Like it's for every epsilon greater than 0, there is some time when you can come within that epsilon of measuring at the other vertex. That's pretty good. But once Chris gave a talk on pretty good state transfer, and afterwards he asked his student, who was not me, it was Dave Robertson. He asked him how was it? And Dave said, it wasn't perfect, but it was pretty good. And Chris did not get the joke. He just walked off saying, oh, sad. So yeah, don't do that to your supervisor. So yeah, it turns out this was a good definition because he worked with these other people. Kirkland is also a spectral graph theorist. Simone Severini, I think at the time he was a postdoc in Waterloo, and now he's a director of Amazon Quantum Web Services. And Jamie was one of Chris's PhD students. So what they found for this situation, for the pretty good state transfer, is that the path on n vertices admits that thing if and only if n+1 is a prime, twice a prime, or a power of 2. So I think that we can distinguish between one bigger than a prime, twice a prime, or a power of 2. So this is like a prime detection algorithm, but quantum, right? Because then you can just build the thing and then run the thing and check if there was pretty good state transfer, and then you would have a quantum algorithm for prime detection. This is pretty cool, but not exciting because prime detection is also in polynomial time classically. So yeah, not groundbreaking, but still pretty cool that there seems to be number theoretic things connected with this property. Okay, so sometime later, Gabriel Coutinho, one of my co-authors, and I, we realized that they only checked for pretty good state transfer between the ends of the path, the 2°1 vertices of the path. They did not check if it could happen in internal vertices. So with another one of Chris's students, we went and investigated this, and Christopher actually finished off the characterization during his PhD that you can have pretty good state transfer between internal vertices if and only if n+1 is 2 to the r times p for some r where p is a prime. So this is consistent with the previous thing, and it sort of fills in the rest of the number theoretic things. Okay. But when we talked again with some physicists, and they were really keen on the paths. They really want to transfer the state from one end of the path to the other end, indeterminate of how many vertices are in the path. So then they posed this question. P4 did not have pretty good state transfer or perfect state transfer. So what they said is, okay, we have this P4. It doesn't have any of the state transfers you studied, but maybe I let you put some loops on the ends, on the blue vertex and the red vertex, such that there becomes perfect state transfer after I put the loops. And, you know, we can let you put any number of loops. You can put a transcendental number of loops. Doesn't have to be integer number of loops, just some weight on these two vertices. Okay, but the same weight, which is actually necessary for perfect state transfer. So you put alpha loops on the vertices, but alpha could be anything. And they conjectured that for any path, you can always find alpha such that there's perfect state transfer from the red vertex to the blue vertex in Pn. So this is a conjecture. They did some computations. They thought it was true. And then this Harvard team with Kempton, Lipner, and S.T. Yao, they showed that this is not possible for any n greater than 3. So very false. But these people, they were still noticing something. It's not perfect state transfer, but they were still noticing some phenomenon in their simulation. And what were they noticing? They were actually observing pretty good state transfer. So in fact, what Kempton, Lipner, and Yao show is that for any n, you can always find values for alpha such that there's pretty good state transfer in Pn. It's very successful. Great. Different alpha, so they give a condition on alpha such that there would be pretty good state transfer, and then they exhibit that many numbers have this alpha. And what we do is like a weighted graph, and there we find that the values for alpha are dense in the reals. So it's there are many choices. Yeah, but for different alpha, yes, some other alphas you don't have it. if you don't satisfy their condition, then
Different values of alpha.
oh, that is not possible for perfect state transfer because you need the two vertices to not just be cospectral, but also strongly cospectral, and it cannot happen with different weights. So yes, you have to choose. Yeah. So then Chris and I got together with two of the authors from the previous paper, with Kimpton and Lipner, and we thought, okay, we can use some more hardcore linear algebraic methods and do some more things. So what we decided to do was this alpha beta perturbation, where we have a graph, and then we have the two vertices between which I want to force there to be some state transfer. And we put alpha between them, I mean, on each of them, alpha loops, and then we put beta edges between them, the beta parallel edges. So we're weighing the matrices. Okay, so we add this small perturbation, small ring 2 perturbation to the adjacency matrix, and then we want to create hopefully perfect state transfer. Okay, so then what we looked at is a class of graphs called strongly regular graphs, which maybe we don't have time to talk about, but they're very nice graphs algebraically. If you are a graph and you look at the adjacency matrix and has just one distinct eigenvalue, then it has to be the empty graph because the trace of the adjacency matrix is 0, so then they all have to be 0. If you have two distinct eigenvalues and you're connected, then you have to be the complete graph. And if you have three distinct eigenvalues and you're regular, then it has to be a strongly regular graph. So in some sense, this is the sort of the graphs that have as few eigenspaces as possible, but it's still interesting. But there are many infinite families and many examples. There are, for example, 11 billion strongly regular graphs on 57 vertices coming from Steiner triple systems 2, 3, 19. So anyway, there are many examples. And what we showed is that if I take any strongly regular graph coming from an orthogonal array, then there does exist alpha and beta such that I can force the new graph to have perfect state transfer. Yeah, this is sort of an ideal case to study such a perturbation because this thing had only 3 distinct eigenvalues. When I do the perturbation, the top eigenvalue goes away. We have the 2 littler eigenvalues with smaller multiplicity, and 5 new eigenvalues are introduced, but they are sort of very easily controlled so that we can still control the spectral behavior and improve this result. But what is even better is that for any strongly regular graph, you can always force it to have pretty good state transfer between my target vertices. And in fact, the good values for alpha and beta are dense in the rails. So it's not very hard to come up with these values. Okay. So that's sort of the end to this perfect state transfer thing from some time ago. And now let's look at discrete time quantum walks, because I feel like they're closer to hypergraphs in their methods, and because now we can look at different pictures. Okay, so there are many models of discrete time quantum walks, and most of them that have significant papers devoted to them fall in this 2 reflection model. That so we recall our previous situation that we just want to study some transition matrix U. And there is a specific scenario. So this is our discrete time quantum walk, that there's a starting state, and then we consider U times the starting U squared. This is how we evolve the walk on the system, and only at discrete times. Okay. So now this U, there's a specific scenario that it comprises of 2 reflections. So P and Q are projection matrices, and then you have U written as a product of 2 reflections. And this is a scenario that we consider to be to be efficiently implementable. So what is really happening is that P is a projector with some dimension, and Q is a projector onto some other subspace. And if quantumly you're building your computer and you can implement measurements on the subspace of P and of Q, then you can also implement this quantum walk. And if you want to build any algorithm at all, you do need to finish your algorithm by measuring. So the minimum things that you need to implement is just measurement. And if you can implement that, you can already make this reflection So that's sort of the reasoning behind why this is a popular model, because you can actually build it even now with our existing quantum computers, that it's implementable. Okay, but for us mathematically, this is just given to us, and then we work with matrices. Okay. All right. So usually people work with different choices for this first projector, but the second projector, you almost always take it to be the arc vertex incidence matrix. So you have, you have the incidence matrix of, you replace every edge by 2 arcs, one pointing in each direction. And then you have vertices versus arcs, and you have a 1 if this arc has this vertex as a head vertex. It points into the vertex. So then quite frequently we take Q to be this projection. And then P, there are many choices for P. Okay. And Chris and Harmony recently wrote a book where they explore many choices for P. And one of the things that they have in their book is this graph embedding version where, so these discrete time quantum walks, they do happen on graphs, but you need to provide it sometimes with more information than just the graph itself, because you need to populate 2 matrices there. And from that P matrix, from that Q matrix, you can already reconstruct the adjacency matrix with the information of which arc is the reverse of which other arc. So the extra information we require for our model is that it's a graph together with its embedding on a surface. So maybe I don't want to say too much about it, but we want to draw graphs on surfaces so that the edges do not cross, but we also want the drawings to be meaningful, to use the surface meaningfully. So if I just drew an edge on the torus in this way, it's true that there are no 2 edges that cross at a point that is not a vertex, but this is somehow like not me using the surface meaningfully, because I could have just drawn this on the plane. If I cut out this bit here, it would have been just embedded in the plane. And what we want is a cellular embedding or 2-cell embedding. So this would give an example of a 2-cell embedding, that it is meaningfully using the surface, or precisely you want that every face is homeomorphic to a disk, which is the case in that embedding. Okay, so you want to draw on orientable surfaces such that edges do not cross, and you want to use the handles in a topological manner. And then this divides the surface into regions called faces, and every edge is on exactly 2 faces. So you have the situation that I look anywhere in my embedding and I have F1 and F2. So when I replace the edges, when I replace each edge with an oppositely oriented pair of arcs, I can say very naturally that this one belongs to F2 and this other one belongs to F1. So now I can make an incidence matrix of arcs versus faces, where this one is incident to F2 but not F1, and this one is incident to F1 but not F2. So now every edge will be incident to just one face. Every directed edge is incident to just one face, and this is how I construct my other operator, my other projector P. Okay, so pictures, right? So it was generalizing things on the toroidal grid, and we do consider the toroidal grid in this example, and we determine certain state transfer. Okay, but let's look at the picture. This is a 4x4 grid embedded on the torus. Right, we accept this is a torus. You glue this edge with this edge, and then you glue this side with the other side. So we are in the universe of Pac-Man, that when you go here, you end up over there. It's okay, everyone is cool with Pac-Man? Okay, so now the quantum walk will move in the Pac-Man universe. So our starting state is like this, that we have an equal superposition around the arcs that come out of this vertex. And we have used red here to indicate the amplitudes that are positive. So the entries of the U matrix, which are positive numbers. Okay, so after one amount of time, it looks like this. So we are in some state where we're not where we were before, and you have some negative entries and some less red entries, so smaller entries. Okay, and then after 2 units of time, it moves. 4, 5, 6, 7. Yes. And after 12 units of time, a small miracle has occurred. It went back where it started. And had it gone to this configuration, but at another vertex, we would call that perfect state transfer. And this we would call periodicity because it's periodic. It went back to its original state. Okay. And then, of course, it continues some more. Okay, so our definition of perfect state transfer is still vertex-based, that you often on the discrete walks, you are evolving around all the out arcs at a specific vertex. So in a state that looks like this, and you wish to move to a superposition around some other vertex. So in our diagram, we want that, but we want it to have happened to a different vertex. Okay. So what do we do in this case? Well, this is a bit more difficult than the continuous time case. And what we did is we projected down to these B sub t matrices. Sorry, this is a small t, not a large t. And so now you have, for every time, you have a smaller matrix that is the size of the adjacency matrix for each time t. But the issue is that B sub 2 is not like B1 squared. It is some other relation. What you want, so we can show that you have perfect state transfer if and only if you have this entry in your B matrix at that time. Okay, so then what I showed with my PhD student in his first paper is that even though it's not true that B2 is just B1 squared, that's not how the matrices work, it is very close to that BT is T sub T in variable B1. So it is the Chebyshev polynomial of the first kind evaluated at B1. So these are all pairwise commuting matrices, and you only need to diagonalize B1. And then you apply the Chebyshev polynomial to it to get the other eigenvalues of the other times. And this was really useful. And maybe this is where I have some connections to hypergraphs, that if we consider any matrix M, so not the matrix M previously, if I want to look at the eigenvalues of MM transpose or of M transpose M, which only differ in the zero eigenspace, then really the decomposition of the space of the vector space that I want to look at is the column space of the matrix M, direct sum with a kernel of its transpose. And then what you want to do is to, over each of these spaces, these are going to be MM transpose invariant subspaces of R, and they can decompose into eigenspaces. And this is sort of how we are proving our results. If this is a very familiar situation for many of you, because if you take this to be the signed incidence matrix of an orientation of a graph, then you would get the Laplacian matrix. If you take it to be various boundary operators, then you get the combinatorial Laplacian for simplicial complexes. And with Sebi and two of his students, we are also looking at clique complexes, also by breaking down the vector space into various invariant subspaces. And here, our situation is a bit more complicated because we actually have two matrices. We have MM transpose and NN transpose, and we're going to multiply them. So our space decomposition is a bit more complicated. But the primary thing, sorry, this is a typo. Oh, no, it's correct. Whew. But it's missing transposes, that we break into a direct sum of two subspaces, one of which is just the intersection of the kernels of M transpose and N transpose. Sorry, there's no transposes. And the other subspace is a span of the column spaces of these two things. And you can show this is a decomposition of the whole space into two subspaces. And then if you consider that U matrix over each of these spaces, this is how we diagonalize it. So over this thing, U has to have eigenvalue 1, which is very simple. And then over the span of the column spaces, this space is U invariant. And in fact, you can break it down into root spaces of 2 dimensions, where U has a degree 2 minimal polynomial over these root spaces. And so you don't need to find explicit eigenvectors, but you have like a 2-dimensional space over which you know you have 2 independent eigenvectors, and you know what the eigenvalues are. And that's what the main tool that we use to prove our spectrally dependent results. Okay, so yeah, 5 minutes left to maybe move to this retrospective of perfect state transfer. Okay, so I feel very lucky because I got to watch this field evolve and participated in it as it was evolving and people were doing research in this field. So at first, when the physicists asked us the question of we would like to make perfect state transfer in a graph, how do we do it? We didn't really know. And there were many papers where they looked at a specific class of graphs like Johnson graphs or hypercubes or just the path. And they were able to come up with some sort of theorem recipe like this, that if you are that type of graph, then you have UVPST if and only if some properties hold. And one of them is that these vertices have to be strongly cospectral, which I unfortunately didn't have time to define. I'm sorry, but they have to be very similar. They have to be mapped to each other via an orthogonal matrix that commutes with A and satisfies additional conditions. And so you need the two vertices to be very similar. And then you need the eigenvalues to satisfy some conditions, some parity conditions. So in the first few things, people characterize perfect state transfer for Cayley graphs. And there it's easy to say when they're strongly cospectral. And this condition is not very difficult. And then people did this for Cayley graphs over cyclic groups, and this was Cayley graphs over Z2 to the n. So these are, for example, hypercubes are covered here. And there were many papers that sort of had a result that looked like this in the end. And sort of people looked at this, and you can make a more general result. So what we did in 2014 with Chris and Frederick van Hove and Gabriel is we looked at graphs that belong to an association scheme or distance regular graph. These are you can consider them to be very symmetric graphs and have very nice spectra. And then this is the thing that we found, in that there is this big condition which tells us when the vertices are similar enough such that perfect state transfer could occur. And then here, this is the eigenvalue condition in this much more general setting than just Cayley graphs over Z2 to the n. So this is the condition that we found. And you can determine whether or not the graph has perfect state transfer at some time just by computing some stuff about the eigenvalues. So you only need to be given the graph and the eigenvalues and the eigenvectors or the eigenmatrices to determine if it has PSD. You don't need to check infinite amounts of time. Okay, and then Gabriel in his PhD thesis, he finished it for all graphs. And if you look, the condition is almost the same that we had for association schemes, except there they can only be integers. So it's easier. And yeah, so this is how a characterization arises. If we were studying PSD like in the beginning, I think this statement would be very difficult to come up with because it has very many technical details. But it was nice to watch it evolve, that people prove easier versions of this for easier classes of graphs, and then you prove it for increasingly more complicated classes of graphs and increasingly complicated statements. And then this is a correct statement in the end. So with my PhD student Vincent in our next paper, so we do carry this to the vertex space model and to also more general two reflection models that satisfy some hypotheses. So we can characterize perfect state transfer and another notion of high state transfer. And then it also supplies us with the time of the state transfer, which is useful for new algorithms. So this is sort of like our contribution to the story of PSD. Our classifications, our characterizing also is very long. It looks very similar to the previous slide, but with more conditions. And I think that like a result like this, it's not possible to imagine how it will look unless you have seen the previous result. So yeah, this is sort of the story of the evolution of this field. And yeah. In summary, we can study quantum walks using linear algebraic methods that are common in algebraic graph theory, and we can bring them to this new place. And you can prove properties about the walk, such as various state transfer and mixing properties that I didn't talk about in the talk. Yeah, it's a good area for applications. And in doing so, various new and also completely classical graph properties and graph parameters and graph invariants arose, and they provide interesting combinatorial problems. And maybe the same is true for hypergraphs. So let's end here. I'm tired. All right.
Thank you, Krystal, for the pretty good talk.
Thank you.
Any questions? Jürgen?
If you try to formulate it somewhat differently, you have somehow a dynamical system on a discrete state space, and you look for periodic orbits or almost periodic orbits.
Mhm.
What properties in general does this dynamical system have in terms of hyperbolicity or whatever you want to know about the dynamical system?
So sorry, I didn't understand. You're running the quantum thing on the dynamical system, or you're trying to view the thing as a dynamical system? But the quantum walk is, so it is shown that if you consider it to be a Markov chain or some sort of stochastic process, it will not be ergodic and it is reversible. So it is a very strange situation if this were to converge. So it will never converge over time. It will just oscillate in its almost periodic state. Oh, yeah. So there is something that can be done like that, but it seems not better than just looking at the eigenvalues of the graph. Yeah, for the periodic orbits, this is Gabriel and some other co-authors, they wrote this paper about irrational quantum walks, about these irrational values. And the picture I showed was C5 and this thing and the flower-looking thing. So there they're really considering it as a Markov chain and showing the almost periodicity of this entry. So you can consider each entry to be.
In those cases where you get this
Perfect state transfer, then it is actually periodic.
and so we want to see which abstract property of the dynamical system is.
But this U matrix has complex entries and it is unitary. So there's like, yeah, you kind of need to rebuild some parts of this theory to accommodate that because it's not a real system. So, and you have this mixing matrix, but it's a different matrix for each time that is not obtained by squaring the previous one or taking the value. So it's, yeah, there are difficulties in trying to consider it and using Markov chain things, methods from Markov chains, that there's like severe difficulties in doing that. But people have done it the other way, that they have already a Markov chain and they evolve it in a quantum manner instead of in a classical manner. That is apparently very fruitful and it's a good method for attacking the quantum search problem.
Thank you, Krystal.